After we explained the testing hypothesis rationale using the gambler on the drawing board, I'm gonna go over the lecture in the slides, hoping that now you can make sense of the slide. All right, so this is just a revision of the probability of getting a 6. And what if you get a lot of 6s? The probability is there. So if I ask you someone toss the dice 10 times and they get 6 on all the tosses, would you say the dice is fair or not? Probably you say not. Same rationale than the gambler. The outcome that you're seeing is not expected. You don't expect to see a lot of 6s in a time, and therefore you suspect that something is happening. And therefore, if a person tosses a dice and gets a 6, you would have no ground to suspect that the dice is forged, because that is just only one toss, and the probability of that is not there. So this is the testing hypothesis. I'm just trying to put the steps back here. Assume the dice is fair, calculated the probability of 10 6s. The probability was too small, and therefore we rejected the assumption. So why for 10 6s we decided the probability was too small, and for a single 6 we said the probability is okay? Where do we draw the line between what is a large probability and what is a small probability? We draw the line at alpha, and I mentioned that previously that's at the 5%. If nothing else is said, that's the 5%. You can draw it at 10% and 1%, but here, I mean, something has to be said so that you realize that alpha is 1 or 10%. But if no one says anything, that alpha is usually 5%. The probability that we calculated, we call this the p-value. And by comparing the p-value to alpha, we decide if what we observed is rare or not rare. So right at the beginning, we have to start with the assumption, and that is that the dice is fair, and therefore we call that the null hypothesis. But you also have to get yourself ready in case you're going to reject that null hypothesis by getting an alternative hypothesis ready. Okay. So the null hypothesis and the alternative hypothesis are complement of one another. Together they define everything. And therefore, if you say the dice is fair and the null hypothesis, your alternative hypothesis has to be the dice is not fair. You do not specify how not fair. You just leave it open. Also, when you calculate the probability, most often before we get the p-value, we need to calculate a test. Remember? Most of the time, you just cannot jump to the probability directly. You need to calculate a z or a t. And by calculating the z and the t, you're going to calculate, you're going to get to your p-value. But just remember that the p-value, the definition of the p-value, is the probability of as extreme as, given that the null is true. Okay? The final conclusion, there, if you put the words, what you have came up as a conclusion. Okay, so here are the official 7-step of testing hypothesis. First, you define your null hypothesis and your alternative hypothesis. Remember, the null hypothesis, you're going to have an equal sign. The alternative hypothesis, you're going to have not equal. As long as you're taking statistics 205 or biostatistics 205, that's how we're going to do it. Is that the only way that it's done? No. There's something out there that is called directional. We're doing the non-directional. We're just considering either null hypothesis I have equal, or and the alternative hypothesis is not. It's going to be not equal. The other thing I want you to remember when you're writing the null hypothesis is that you're going to use population parameter, not sample statistics. The null and the alternative hypothesis are written using population parameter. The second step, you assume the null is true and you set alpha, and as I said, if nothing is mentioned, you set alpha at 5%. Step number 3, you're going to collect your observations. You're going to look at your sample, If you're running an experiment, you're going to run your experiment, and based on the results of the experiment or based on your sample, you're going to use the results, the observed results, to calculate a test. So it's either a z-test or a t-test, depending upon what you're doing. Step number 4 is that you're going to use that test to calculate your p-value. Again, let me remind you what a p-value is: probability of observing results as the one you observed or more extreme. In other words, probability as results as extreme as the one that you observed, with the condition that the null is true. Okay? Once you calculate that p-value in step number 5, you're going to compare it to alpha, and if it's greater than alpha or less than alpha, you're going to reach your statistical conclusion. Your statistical conclusion is either reject the null hypothesis or fail to reject the null hypothesis, which takes you to your final step, and that is your research conclusion, where you're going to have a conclusion that everybody can understand. So here's an example. A drug company making vitamin C pills claim that the pill contains 100 milligrams of calcium. You know, calcium is needed for the absorption of vitamin C. We would like to put this claim to test, and therefore we took a sample of 25 pills and we sent them to the lab, and the lab came back with an average concentration of calcium of 92. So the X bar was 92. The drug company was claiming that mu is 100. We observed an X bar of 92, and we're willing to adopt a sigma of 18. Using this information, we would like to know if the claim of the company holds or does not hold. Okay? All right, so let's see how we can test that hypothesis. Well, if you remember, your step 1 is your null hypothesis. Your null hypothesis is you're going to take things at their face value, meaning you're going to say, okay, well, if the company say it's 100, I'm going to believe it's 100. So you're going to write the null hypothesis. The average concentration of calcium per pill is 100. And notice you're writing mu. You're not writing X bar, because you're saying in the population of all pills produced by this company, the average is 100. But just in case this is not true, we're going to get ourselves ready by having an alternative hypothesis, and that alternative hypothesis looks exactly like the null hypothesis, except that instead of having equal, you're going to have not equal. Okay? And both are complements. So the reality is either the null or the alternative. That's it. There's nothing else. Okay? All right. So what we're going to do is we're going to assume that the null is true. We're going to accept the claim made by the company. We say, okay, we believe you. And before we do anything else, we're going to set the alpha at 5%, meaning that if the probability came out to be less than 5%, we're going to declare that to be rare. And if it comes out to be greater than or equal to 5%, we're going to declare it to be not rare. All right, so step number 1, step number 2 done. Let's move to step number 3. To step number 3, this is the bridge between the results and the probability. We just cannot jump to the probability. We need to be able to calculate the probability. We need to calculate a test, and that test is going to help us get the probability. All right, so what do we have? Well, we have a sample of 25 pills, and the average of that 25 pills came out to be equal to 92. Okay, and so we need to ask ourselves, what is the probability of getting results as extreme as an average of 92 in a sample of 25 if the null is true? That's what we're trying to do. We're trying to say how likely is it to get an average of 92 in a sample of 25 if in reality the null is true. Okay? So to be able to answer that question, we're going to calculate a test. Okay? So what is the probability of getting 92? Okay, so what we're saying that if the null is true, the sampling distribution of the means is normal. Now, how do I know that the sampling distribution of the mean is normal? One of two things. Either my sample size is greater than or equal to 25, so that the central limit theorem applies. You already know that. In that case, it is. My sample size is 25, so I'm safe. Or I have to say that the concentration has a normal distribution. Now, since here I have a sample size greater than or equal to 25, I'm fine. I can already know that the sampling distribution of the mean is going to be normal. If the null is true, the average of the averages, the mu x bar, is going to be equal to 100. And the one I observed, 92, is right here. And therefore, the probability I need to calculate is how likely to get a 92 average. And therefore, what is the probability of getting an average, an x bar, as extreme as 92? If you remember, as extreme as means you go to 92 and you're going to go away from the mean. So you need the blue tail, but you also need the yellow tail. You need both tails, because we covered that previously, that as extreme as are both sides of the distribution. So by calculating the blue, you can just get the blue and multiply it by 2. That will give you the blue and the yellow, okay? So how do we get the blue and the yellow? Well, we're going to use the Z. Why are we using the Z and not the T? Because we were provided with the sigma, okay? All right, so how do we calculate the Z? Well, the Z is x bar minus mu over sigma divided by square root of n. X bar is the value that we observed in our sample, which is 92. Mu is the population average provided by the null hypothesis. Remember, that mu was given to us by the null hypothesis. And since we started our work with the assumption that the null is true, I can just plug it here. I can do that. Then I'm going to divide by 18, and that also was provided to us, divided by square root of the sample size, which was 25. By doing so, I've calculated a Z that is equal to negative 2.22. Okay? Now, to get that is step number 3. I got my test. Now I want to move to step number 4. Step number 4, you're going to get to use that Z to calculate the probability, which is the p-value. Okay? Remember, the p-value is as extreme as. And therefore, since your Z is negative, you're going to take the probability of Z less than that negative value, because remember, you have to go down. So I'm going to go up 2 slides now just to remind you of the distribution, and I'll be back